Okay. Broadcast live. We are sending live. Okay. In this video, I will continue the development of my motor drive, and I'll be setting up the device tree for the motor drive chips here, which connect to our MCU, using several control signals and analog signals as well. What we need to do first of all is just map both drivers in the device tree to the appropriate GPIO pins on the microcontroller. So that's what I'm going to do first. Let's start with driver number 1. In the device tree, I'll define a section which will describe the motor drive chips. And I still don't have the driver actually implemented in software, so this is just kind of getting an idea of what it is that we want to achieve. And once the device tree once I've put the sections in the device tree, I can start writing the code that will actually read the sections and configure all of the peripherals that are involved in driving the DRV8302 chips. And I'm just thinking, because this is going to be very highly dependent on STM32 peripherals, because it's going to be configuring timers and the ADC, possibly a few other things, possibly DMA as well, and that is very specific to the STM32. So there is likely going to have to be several implementations of this driver depending on the version of STM32 that we are running on. So I think I'm going to be placing this in the more hardware-specific code. Or I'll actually decide that a bit later. We'll see what different parts we have first, because there's both there's possibility to use this as a BLDC driver and also just as a DC motor driver, and even for driving other types of loads. And the configuration of the timers will be different depending on which type of load that we want to drive. So it's quite possible that I would actually have the code separated into multiple drivers, where I have the most basic hardware stuff defined in the hardware-specific code, and then the higher level stuff, such as BLDC driving code, can then be defined in a more generic code. However, there can be certain issues with doing that, and the most obvious issue is that this is quite a real-time task to control the motor, so it's likely that it will need to be implemented directly in the interrupts. And the question is then whether separating this into multiple drivers is really that good of an idea, because it does create a certain latency compared to directly putting this code into the interrupt handlers. So that's something also to explore in this video, or not in this video, but in this video series. So hopefully we get everything sorted out pretty soon. Alright, we have the overcurrent warning pin. It goes to here somewhere. I wish I could kind of like select this label and get like lines going to any other connection that connects to this label. DF9. GPIO F, GPIO and or is that's actually an input, because that's coming from the DRV chip. Let's see, mode. What other modes do we have? And I think we need to have a pull up here as well. GPIO up. I have a feeling that this is going to be quite a boring video, just defining the device tree nodes for all of the pins. Hopefully I can make it a bit more valuable by actually explaining what each pin does. So we have the fold pin, which is going to be it's an open drain, or actually, yeah, I think it's an open drain pin, it will go low when there is either overcurrent fault. So first of all, when current rises, overcurrent warning will go low, and then when the current rises above the overcurrent protection level, the fault pin will go low. And also this pin can go low if there is let's see, I think there is a few other conditions when it will go low. It could be that I'm actually not entirely sure what other conditions that trigger this pin, but this pin indicates that there is some problem with some signal that's going into this chip or going out of this chip. And the way we respond to this is by I'm pretty sure there was some way to reset the fault. Actually, I feel like checking this out. I'm a bit curious myself. So let's see. Right, so we reset the fault by toggling AND gate. And there is under voltage protection, over voltage protection, and over temperature. Right, so that was another thing that would toggle the fault pin, over temperature. Fault and protection handling, we have, yeah. So this is all of the different faults that can be detected by the chip. Okay, anyway, so just setting this pin to input, very similar to the overcurrent warning. And this pin is connected where? PF10. And next. Actually define all of these pins. I'm just going to make sure that all of them are defined in the same order in the motor number 2. Let's see here. So we have AND gate, DC cal. Let's see, we have 11, 12, 13. AND gate, DC cal. Mode for the overcurrent protection. DC cal allows us to read the 0 point on the current shunt amplifiers. Enable gate basically enables or disables the gate driver, and MOC is mode for the overcurrent protection. And all of these are outputs. Oh, I forgot the gain. That's actually the gain. Gain can be set to either 20 or 40 volts per volt on the current shunt amplifier input. So for every volt across the current sense resistor, we would get 20 or 40 volts on the output. So naturally, because the voltage on the current sense resistor is very small, the output voltage will just go up to the reference voltage, which is 3.3 volts in this case. So, gain and MOC. So all of these pins are basically GPIOs, so that's simple. And I wonder if there are any others that I need to take care of here. Besides, of course, the driving inputs and the current sense analog pins. So in terms of normal GPIOs, I don't think there is anything else that needs to be connected here. So next on the list is how to solve the implementation of the actual PWM inputs for the MOSFETs. And also we have this circuitry here that senses the voltages on all phases, which also will need to be fed into the specific motor driver, whether it's a PMSM motor or like brushed mode, if it's going to run in brushed mode. If it's going to run in normal sensorless mode, or if it's going to be using encoder. And I think that probably I will implement, if I can, I will implement those things in smaller separate drivers, and then reference them through the device tree in the main device driver for the motor. But I think it could actually make sense to expose the interface to these pins in terms of the voltage level that we're going to be outputting, because we're going to be modulating this as a PWM, but essentially to the higher level driver it appears just like a voltage level. And we could expose the current sensing maybe as well, since the current sensing, in this case, current sensing is part of the DRV chip. So current sensing in this case depends on the DC cal value that we read when we set the DC cal to high, and the values that we read here as 0 points. So we need to put this code in the driver that is responsible for the DRV chip, because we need to be able to calibrate the readings on these pins. So I think I'm gonna just basically start by I could start defining these pins, but they have to be defined as both the GPIO configurations need to be defined, and also the timer configurations need to be defined. So whether we are going to be using timer 1 or timer 8, because we want to use the same code for both drives on this board. So I'm going to start by defining just the GPIO configurations. So we have in HA2. Let's start with 1. And we have in HA1 PE 8, 9, 10, 11, 12, 13. We also have the break input we can define here as well. Or actually no, the break input is going to go to the, let's see. No, actually the break input has to go in this driver, because it is related to the timer that we use to control the motor. Okay, so this will be GPIO mode AF, and we can define it similar to this definition. So we'll have AF, then the name of the timer, and we're going to be using push-pull, and we could use 2 megahertz. So the reason for setting the speed of the I/O is that if you really need high-speed I/Os, then you set 50 megahertz. But that setting affects the slope of the waveform that you're generating. So if you set the speed higher than you need, then you're gonna have unnecessary EMI on the PCB traces that carry that signal, because you're gonna have much faster slope. So it can be like a general recommendation is to use the value that's as slow as possible. And in this case, we're going to be running at 30 kilohertz, so we don't need anything above 2 megahertz. So we can set the I/O speed to 2 megahertz. Yeah, and we don't need to set mode AF is only for STM32 103. So this will be directly set to AF TIM1. And GPIO GPIO type. I think this should map the pins correctly. LCHC. Alright, so that's that's our GPIOs, and then also the break input will be PE15. PE15 will be connected to timer. I think it needs to have its AF function set to timer 1. And it's going to be an input. And we're going to set the pull up there as well. All right. So the question is now if we could expose this as a generic, kind of like an analog interface. So another thing is also that both the voltage sensing and the current sensing needs to happen at specific points during the PWM cycle. So essentially, it's this driver, the same code, has to also control sampling of the voltage sensing inputs. So it's very hard to separate this code. I've tried to do that several times before, but usually it just ends up, everything has to go and like to be very tightly knit together in order to satisfy all the timing requirements for doing this type of thing. Let's configure also the analog pins for the current sensing. PA3 and PA4. That's going to be on ADC 1. I've documented the channel mapping here. Actually, it's going to be, yeah, it's going to be on ADC 1. PA3 and PA4. And I wonder if it's enough to just set this to like analog in. So then it's mode and and 10, 11, 12 would be the voltage sensing. I'm going to define the voltage sensing for now as well. So PC0, 1, and 2. All right. So next we also need to define the actual timer that we're going to be using. We can do it like this, team1. And so basically by the preprocessor, this will be converted to the actual address of the team1 peripheral, which we can then just cast to the timer tim type, like tim type def, I think. So it just becomes the pointer to the timer peripheral. The ADC ADC1. I think it's probably a good idea to just keep all of the signals on the same ADC for each motor. So I did map a few things a bit differently. I think I'll need to revise that. Yeah, and of course the encoder as well. Encoder can actually be a separate driver. The only tricky part here is that there's certain things that need to happen in the motor drive driver to as a response to changes in, for example, the Hall signal, and they have to happen very quickly after the change in Hall signal. Trying to separate this code into multiple drivers will become problematic, I think, considering that it has to be very short response times. It has to be very real-time. Code is designed to run in real time. But I could define the pins here right now, and then maybe move them to another driver. PA15 and PP3. We don't need the speed setting for inputs. And this is not strictly necessary, but I'll define the pins as inputs here anyway. just to make it more clear. So is it Team 3? Or are we using Team 2? Yes, it's Team 2. And HAL will connect to PA0102. And that will be Team 3. It would be a very clean approach to implement this as a separate driver. But we are still gonna have to have some form of quick notification to the motor driver about any errors that occur on these lines. So because we want to read the errors and they have to be read over SPI, this is not going to be happening in real time, but it still needs to happen, and then the notification still needs to get to the driver that is responsible for a specific type of motor that we're running. So I still need to figure out a good way to deliver these notifications in a kind of as quickly as possible, even though in this case not in real time, still as quickly as possible. And the same goes for any changes, for example, in either the encoder inputs here or the HAL sensor inputs that go to timer 3. I think that the most reasonable approach is actually that I'll implement, I'll configure the timers for generating the PWM, and start from there, make sure that this chip works, make sure that I'm getting some waveforms on the MOSFETs, and then while I'm doing this, I can also keep in the back of my head how I'm going to implement the code for all the other things that relate closely to the motor control task. So that sounds like a good plan, I think. And it's going to be fun. It's going to be time to see if the MOSFET drive is properly designed and actually works. So de-risking that and verifying that is going to be the next step. Okay, I'm going to stop this video now, and I'll see you later.